This is Fundamentals of Micro and Nanofabrication. I am Swayam Prabha from IIT Bangalore, and today's lecture will focus on ion implantation, which is one more method in which we create dopants inside silicon. Okay, so let's get started. So the basics of ion implantation are fairly simple. You take a wafer, and instead of diffusing ions, which is what we were trying to do in the last lecture, we will shoot the ions at the substrate with a lot of speed. The way we do that is we take an ion source. This ion source would change with the dopant. So supposing you were doing phosphorus dopant, then this ion would be phosphorus. If you're doing boron implantation, this would be boron. And since we are talking about the ion, it carries a certain charge, and that charge can be used to accelerate the ion at very high speeds. So you put some electric field, and because of the electric field, the ion is now attracted towards the substrate. And if this is in the vacuum and the mean free paths are long, then ion will not lose any energy during this process while it goes from the source to the silicon, and in some sense bombard the surface, very similar to how sputtering bombards the surface. Because the ions are flowing, you can measure the flow of ions through some current source, and that is, in very rough sense, is the basic of ion implantation. So ions go, they collide with the substrate, and because of their very high speed, they penetrate the surface. They don't just sit at the surface, but rather penetrate the surface, creating a layer of doped silicon. One of the issues with this approach, and it was one of the main challenges that ultimately had to be solved before the technique became widespread, was this sort of mechanical bombardment causes damage. Unlike diffusion, which is a very gentle process where atoms automatically come into the substitutional position, ion implantation does not promise that. So you have to do some subsequent anneal to actually make sure that the dopants are sitting in substitutional sites. And if you remember previous lectures, a dopant sitting in substitutional site is the only one that can actually lead to doping, that can actually create carriers. A dopant that is sitting in an arbitrary position inside the lattice, say in an interstitial position, would not lead to doping. Okay. The second thing is damage. You don't just create dopants inside silicon through this methodology, but you also displace the silicon atoms already present in the lattice. And those displaced atoms then need to be put back into their correct position, else you will not retain the properties of silicon. So these two issues, lack of substitutionality and repair, both require anneals. We'll talk about anneals slightly later in the lecture. So this is a more involved diagram that explicitly shows what is happening. So we have a certain ion source, typically thermionically generated. Because they are ions, you can apply an electric field that actually accelerates those. And then there typically is some sort of a separation magnet. This is very similar to how mass spectroscopy works, where you can select a certain mass, where you can sort of detect a mass of ion by putting it a magnet and measuring its curvature. Here what you are trying to do is using the same technique to select an ion of a certain weight and a certain charge to go through. Okay. So things that are a little off, or impurities that are a little off, would not be able to go through. Only the ion with the right mass by charge ratio would be able to go through and get bombarded on the substrate. The substrate is internally connected with the current integrator. So every ion is a charge. So if you supposing deposit 10 ions into the silicon substrate, you know that you will measure a 10 electron worth of charge. So by just measuring the amount of charge or the current flowing in this whole system, you can actually get a very accurate measure of how many ions have been bombarded. This is much more accurate than the diffusion process that we had discussed previously. In diffusion, you just had a model, and based on the model you predicted a certain profile, and any error in the modeling would lead to an error in the estimation of how much dopants you have. There is no explicit control in how many atoms you are going. You just hope that your model is accurate. And as towards the end of the lecture we started to look at, while modeling is extremely well understood, there still are a lot of confounding factors. For silicon we may understand them all, but for an arbitrary material that may not be true. Ion implantation, on the other hand, is intrinsically more accurate. You can actually measure with arbitrary precision how many ions are coming onto the surface. So you can measure with arbitrary precision how many dopants are in the silicon substrate. So for cases where very high accuracy of doping is required, which is pretty much the most modern electronics, ion implantation is superior. Okay. What is the typical profile do you get in ion implantation? It resembles a Gaussian. So again, if I were to put your attention back to the last lecture where we looked at two extreme cases of dopant profiles. One was the case of infinite dopant, in which case we get an error function profile, and one was the case of finite dopant, where we got a Gaussian profile. So, this is also a Gaussian. So, in that sense it is similar. The only big difference is that in diffusion you only get half of a Gaussian. So, you only see this half of a Gaussian, while in ion implantation you actually sort of see the full Gaussian. And one way to understand why that is happening is to just look at the figure here. So, supposing you are getting an ion beam and you have a surface. So, this is vacuum. So, the beam is coming straight without any hindrance, then it hits the surface where it starts encountering silicon ions. And every time it encounters a silicon atom, it suffers a scattering mechanism. And with each scattering, it deviates its path a little bit and it loses a little bit of its energy. And after several of these successive collision events, at some point the energy is completely dissipated and the ion, the implanted ion, comes to a stop. Just clear, these are collisions, this is not diffusion, right? A diffusion also does a random walk, but this is not a diffusion mechanism, this is a ballistic collision mechanism. So, at some point the ion comes to a standstill, and this process keeps getting repeated again and again. Because this is a stochastic process, there is no guarantee, or there is no one depth at which all ions will stop. Some will stop a little earlier depending upon what was the angle of collision, some may go a little deeper. Overall, if you implant a lot of ions, you tend to get a Gaussian profile. Right? So, because the very nature of the process means that you actually see both halves of the Gaussian, there is a certain peak in the middle, and at that peak, whatever the depth you measure is what is called the penetration depth, and then there is a maximum concentration which is called the peak concentration. The measure of how much deviation you have from the projected range or the implanted range is what is called delta RP, which is also called straggle or deviation of the ion implantation. So, unlike diffusion, here the parameters to keep track are what is the straggle of the implantation and what is the penetration depth of the implantation. Right? You keep going further. Here is the mathematical expression for what that concentration profile looks like. So, C as a function of x is Gaussian, as we have discussed. The total number of implanted ions, which is what we call dosage, right? The same thing we also tracked during diffusion. Dopants cannot be created or destroyed, right? So, whatever number of dopants you have deposited inside silicon must be there. So, the area under the curve, the integral of the curve, must be the dose. Now, this dose, as I have discussed before, is very accurately measured. So, this is a known value, and you also notice that this dose is directly proportional to both the straggle as well as the peak concentration, right? So, increasing the dose tends to increase the peak concentration, right? So, peak concentration is directly related to dose. If you want higher doping, you just increase the dosage, you just implant more number of ions. The other things that you can control in the ion implantation is the acceleration voltage, how fast is the ion going by the time it impacts on silicon, and that can easily be controlled by just controlling the various voltages in the ion implantation system. That is what is called the energy of the implant. Okay? So, these are the two parameters that the ion implantation machine controls. It controls the dosage, which is the total number of ions, and it controls the energy. So, more the energy, the more the penetration, and this again is probably easy to understand if you remember this picture, right? So, if the ion beams are coming with a higher energy, they will penetrate more into the surface, and they will on an average take longer or penetrate deeper before they come to a standstill. So, this is easy to understand. The more energy you plant, the projected range or the depth of the implant keeps increasing. The heavier the ion, for the same amount of energy, the more it will penetrate, right? The less it will penetrate, because the heavier ion will suffer a lot of, for the same amount of energy, a heavier ion will have lower velocity, and because the heavier ion will have lower velocity, it will suffer fewer number of collision before coming to a standstill. And this sort of seems intuitive. If there is a big ion, it will have a lot of problem getting into the silicon and moving silicon. If it's a lighter ion, it will sort of just go through. This is what you see in the data. As you go towards heavier ions, say you go from boron to antimony, the projected range reduces for the same energy. So, the energy is the constant, velocity is lower. If you look at the standard deviation of the same thing, more the energy, the higher the standard deviation, which is intuitively makes sense. The projected range is increasing, so the deviation must also increase. And again, there is an effect of mass. So as you go from boron to antimony, you increase the mass, and as you go for heavier masses, the standard deviation reduces. You actually get a more repeatable or a more accurate implant with antimony that you would get with boron. There are a few other general trends you can sort of extract. While the absolute values, of course, nobody expects you to remember these tables. We have simulators for that, which actually have all these numbers stored in, so you can just put in the numbers and extract your profile. But as an engineer, it always helps to have an intuition on what exactly is happening. So the next few slides are just to help you develop that intuition a little bit. So the first thing you sort of see is the thing that we discussed. So if you take a heavy ion, say arsenic, and you take a lighter ion, say boron, it will show you these two types of profiles. So a lighter ion will typically penetrate more, a heavier ion will typically penetrate less. Similarly, a lighter ion will probably have more standard deviation, a heavier ion will have less standard deviation. So the straggle will be lower for the heavy atom, higher for the lighter atom. Similarly with energy, if you are coming with a lot of energy for the same ion, you will have higher straggle. If you are coming with less energy for the same ion, you will have lower straggle. And similarly, if you are coming with more energy for the same ion, you will have more penetration, and if you have less energy for the same ion, you will have less penetration. Okay. Of course, reality is a lot more complicated. There are a lot of other effects that can be. The stochastic process itself is represented by a Gaussian, but that is an approximation. Sometimes the profiles are not exactly Gaussian. And here is an example of these dots are actually measured concentration, and the dotted line is the Gaussian, and you can see it is an approximation. We can try fitting it to other popular profiles such as a Pearson model or a joint half Gaussian, half Pearson model, etc., etc. Things do become, some of them are more accurate than the others, but of course nothing exactly captures the real data. The way this is actually solved is by using simulators. So, and the way the simulator mathematically handles it is that it does not just remember one or two parameters, but it remembers a lot of parameters. So what they do is, for each ion that you can probably implant, you can theoretically measure the first moment. So the first moment of any distribution is the mean. You can then measure the second moment, and the second moment is typically the standard deviation. For things like Pearson and Gaussian, these two moments are enough to perfectly define it. However, for an arbitrary profile like that represented by this dotted curve or this dotted data, you have to now start measuring higher order of moments. So you can measure the third moment or the fourth moment, etc., etc. And the more moments you add, the more accurate your profile will be. So for various types of ions, the simulator sort of measure these moments. So A1 to A2 to A3, A4, A5 are successive moments of the distribution. I will never quiz you on these numbers, you do not need to remember them. This is just so that when you do use a process simulator, you have an idea what is happening. With that, let us come into some complications that you would actually measure in real life implantation. For the first, asymmetry. So what that means is that if you actually go and measure the concentration of say an antimony, arsenic, phosphorus or boron as a function of depth, you would notice that they are not exactly symmetric. So not only are they not exactly Gaussian, but they are not very symmetric either. A lot of them would show these sort of tails like you see in the red and green curve. So you see a sort of Gaussian, right? But then towards the end there is a significant deviation and you see these tails. We need to understand why that happens. In boron, there is another problem you may be seeing. You may be seeing that the concentration is a little over-represented on the left hand side and a little under-represented on the right hand side. It is as if the boron concentration is biased towards lower depth. So why this is? So these are some of the things we shall now discuss in the subsequent slides. So the first important aspect to appreciate in ion implantation is channeling. So, in order to understand channeling, let us first look at a lattice. So, what you are looking at is the silicon lattice, but viewed from various angles. So, supposing you were to look silicon lattice from the 110 direction head on, this is what you would see. You would see hexagons. Okay. If you look from the 111 direction, you would actually start seeing these squares. If you are looking from the 100 directions, you may start seeing these parallelograms. And this is just a visual illusion, or let us say this is just what the cross section of that lattice orientation looks like. However, you may notice that even though silicon has a certain atomic density, the apparent density of atoms per centimeter square looking at these three different orientation is different. The silicon 100 seems to have a slightly different aspect ratio hole than the silicon 110 or the silicon 111. Right? This has an impact on ion implantation, because remember, this is what an implanted ion will actually see on the silicon surface. When the ion comes, the number of atoms that it actually encounters in the silicon lattice will depend upon what orientation of silicon is visible to it. And in the fourth extreme case, you can take this 100 and give it certain tilt, some random tilt, and then you start to see that these holes completely disappear because the atoms are not aligned one behind the other. You actually have a much more and apparently much more dense face of silicon that you actually see. Right? What this leads to is what is being shown in this slide number 12, where the ions are going many successive collisions, but every now and then they will enter this sort of a channel, right? What am I mean by the channel? You see here, this is a channel, this hexagon is a channel, this square is a channel, this square is a channel. A channel is the portion where there are no silicon atoms, because silicon atoms in a lattice will line up one behind the other. So, in between these lines of silicon atoms, you will have a little space, and if the ion is small enough, and a lot of ions are, then they would suffer collisions and ultimately get constrained in this channel. So, they will hit silicon, but then get scattered into sort of get piped into these channels, very much like maybe a light gets coupled inside a fiber laser, right. So, not exactly the same mechanism mathematically speaking, but intuitively that is what is happening. They are just suffering collisions, and every time they collide into a line, they get channeled into one of these channels. What that leads to is that now once the ion is in the channel, it does not encounter as many silicon atoms as it should have if it was in a random direction. And that leads to it going deeper inside the silicon before coming to a standstill. So, what you would notice in the concentration profile is that you are expecting a blue non-channeled profile, but what you would actually measure is a red channeled profile where the depth where the concentration at higher depths is higher. The ions took longer to stop than they would have if you assumed a simple profile. So, this sort of a channeling is a very common effect noticed in ion implantation, and as a process engineer, you should always be wary of it. So, these are some actual simulated profiles. This is from a simulator from Silvaco. I think Centaurus also sells similar simulators, and then there are other companies. And using a whole bunch of existing data from papers and all, they have the ability to give you profiles that are fairly accurate. So, here is a profile that you can simulate, say, for 1 into 10 to the power 15 dose and 100 keV phosphorus implant in silicon 100. And initially it will show you some sort of Gaussian profile, and then because of channeling you will start seeing this tail, right. The open circles are actual data. So, you can see that the simulator does a fairly good job of predicting what the actual profile is going to look like. And you see the such tail at a range of concentration gradients. So, even it's a range of dosages. So, at high dosages you see the tail, at low dosages you will also see the tail. And because the apparent density of atoms at any phase is different, remember 100, 111 and 110 slightly look different when you look at them edge on. So, that would also lead to a difference in probability of channeling. So, if you look at slide 14, compared to a randomly oriented silicon where you would expect a clean Gaussian, if you were to expose a 1-0-1-1-1 orientation or 1-0-0 orientation or a 1-1-0 orientation, you would get very different profiles. The channeling is actually the highest in the 1-1-0 direction because the number of atoms per centimeter square are so low. You have this hexagon sort of cross section which has huge large channels. And because the channels, the profile does not just not look Gaussian but looks completely different. It sort of is, it has a high here, then a local minima, then it goes up and then it comes back down. So, what it practically does is it significantly changes the depth of the implant, and if you are not careful about this, you will end up underestimating the depth of the implant. Silicon 100 is the one that is the most common, and even that shows this sort of a channeling behavior which leads to this sort of a flat profile and then a sudden drop. So, what can we do about this? Well, there are 3-4 things we can do. We will come to that in a minute, but let us first also appreciate an effect of dosage. So, is channeling higher at higher doses or is channeling low at lower dosage? Now, those of you who were paying attention when we were just a couple of slides ago discussing the Silvaco profile, the same data was there, but here I am sort of representing this data again just to highlight the issue. So, let us take, we do a certain dosage of around 10 to the power 15 per centimeter square, and that is this profile, right. So, this is our high dose profile, and you see a second hump which is because of channeling. And supposing you do a low dosage, so the low dosage say 10 to the power 13, this is this profile. So, this also shows you a tail. Now, it is very hard to immediately compare this and this curve because they are at such a high different dosage, and remember dosage is directly proportional to peak concentration. So, the peak concentration of the high dose is much higher. So, the peak concentration here is around 10 to the power 20, the peak concentration here is around 10 to the power 18. To compare that, what I will do is I will scale this curve artificially up, right. So, I will just scale it up. So, I will just magnify this by a certain factor, and that is this scaled version of the low dose profile. And I have done this so that you can better compare these two curves without the confounding effect of change in concentration. So, when you look, you notice that these two curves do have a slightly different shape, and if you were to think if I were to ask you the question which shows higher channeling, the answer clearly is that the scaled version has more channeling than the than the higher dosage case, and that is what the typical profile looks like. The channeling phenomena is higher at low dosage than it is at higher doses. And why does that happen? That is partly because of accumulation of damage. So, as I hinted before, implantation is a very mechanical process, it is a ballistic process. So, every time the ion comes and collides with the silicon atom at that very high speed, it leads to some damage in the silicon lattice, and that damage will accumulate the more ions you bombard, and that damage will subtly move the silicon atoms away from their lattice positions. So, in some sense it is destroying the lattice as we go along, but as you destroy the lattice, you also destroy the channels that exist in the lattice. So, the channeling phenomena becomes less important. So, just because of accumulation of damage, the channeling is a little lower in higher dosages. At lower dosages, you do not accumulate enough damage to significantly reduce channeling. Once again, if I were to take your take your attention back to the first slide where we looked at various orientations, this one specifically, right. So, how did we make this orientation? We simply took the 100 orientation and gave it a little tilt, and that creates and that sort of prevents these silicon atoms to line up and prevents the formation of these channels. So, that is what is a common technique that people do to fix this. So, instead of implanting on the silicon wafer at a 0 tilt, which is what you would do if you were to naively do this process, you can now do the silicon implantation, the silicon wafer at a certain tilt. So, a small tilt, say 7 degrees, and that actually significantly reduces channeling. So, here is some data again. So, the crosses are the data at 0 degree, which is flat wafer, and as you increase the angle, the channeling keeps reducing, and at 7 degrees you sort of get a very low amount of channeling. This data, by the way, is also courtesy of Silvaco, which is a simulator that you can use to find these things. So, this is a very common technique. So, when you this is so common now that this is the standard. So, if you are sending your silicon out for implantation, unless you say otherwise, they will probably do the implantation at 7 degrees. So, if tilt is something that is important to you, or you are doing research in the effect of tilt on your implantation, make sure you tell that to the vendor, so the vendor can actually do that variation and give you implantation at various tilts. Another common method that people use is to grow a screening oxide. So, you are doing an implantation on a silicon wafer. In the simplest case, there is no oxide on top. Supposing you were to grow a very thin layer of silicon dioxide on the top. Now, remember, the silicon dioxide is amorphous, so it does not have any crystal orientation, and if it does not have any crystal orientation, then it does not have any channels. So, even though there are channels below the silicon oxide, the first layer of few atoms that the implanted ion sees does not have any channels, so it does not get channeled. If you may if think about it, the silicon dioxide is sort of diffusing the ion flux, so that ion flux is not incident at one angle, but just gets diffused and has multiple angles. And if the ion flux is coming at multiple angles, then it will not channel as easily. And this is what is actually seen in the data compared to the native oxide, which is just the oxide that grows automatically on the silicon surface. You do not do anything. Compared that to say a 10 nanometer oxide, which is 100 angstrom oxide, the channeling is much lower with the oxide than without. However, this screening oxide does not come without its own challenges. One of the challenges is that the amount of dopants in that silicon becomes a little harder to characterize. So, this is an example from an actual paper. I urge you to go read it, of various implants that were done on a silicon wafer with a screening oxide grown on top. Okay. So, this is your silicon wafer and you are looking at its depth, and on top of that there is around 100 nanometers of oxide. So, now you do your implant at different dosages and at different energies. So, you would get different profiles. To a first order, silicon dioxide and silicon have the same penetration. There are differences, but slight. So, let us ignore that for a minute. So, let us assume the profile would look exactly the same, whether it is silicon dioxide or silicon. So, penetration depth remains the same, the straggle remains the same. So, blue is what you would get at 10 power 14 dose and very low energy. So, because the energy is low, the implant depth is low. Right. Let us look at this red curve. This red curve has slightly higher energy, so the implant depth is more. And this orange curve has the lowest dose of them all, but the energy is higher, so the impact depth is higher. And as you are changing the dosage, you are changing the peak concentration. So, the peak concentration keeps falling as you keep reducing the dosage. Now, after you have done these three implants and you go and measure what is the actual doping in silicon, you would notice that blue does not have much doping at all, and the reason is pretty obvious. Most of the dopants that you implanted are still stuck in silicon dioxide, and if they are stuck in silicon dioxide, then they cannot give you doping. I mean, they need to be in silicon in order to be electrically active. On the other hand, red, around half of the dopants would give you electrical activation, because around half of them are stuck in silicon, but at least half of them are in half of them are stuck in silicon dioxide, but at least half of them made their way into silicon. While in orange, the majority of those are within silicon. So, this sort of mismatch in actual silicon being in of ions being in silicon can make you under or overestimate your doping if you are not careful. So, that is one disadvantage of using screening oxides. The second disadvantage of using silicon oxide is that through this implant process, the damage is also accumulating in the oxide, and in fact, there is a small probability that some of the oxygen atoms from the screening oxide will get knocked into silicon during the implantation process, and then those excess oxygen can again lead to some silicon dioxide clusters in silicon, and that is not good for the device. Yeah, so those are the two main disadvantages. The advantage, however, is that it can be used to tune the profile. So, you can sort of get very different shapes, because Remember this blue curve has a very narrow dopant profile because of the screening oxide, right? So if that is your goal, then adding a screening oxide gives you a way to tune the profile of the implanted atom. And it also protects the silicon atom. One of the challenges in an implant of doing very clean implants is that the whole implanter is typically made of stainless steel. So it's a vacuum chamber, it's made of stainless steel, and the ions are being channeled, right? Every now and then that ion will collide with the wall of the steel chamber, and some of the iron or some other metallic impurity from that steel chamber will now become part of the ion flux. So as the ion flux comes and hits your silicon, those metallic impurities will also come and hit your silicon. And if you have learned anything in this course so far, is that metallic contamination is deadly for silicon devices. So ion implantation is fundamentally a little dirtier process than diffusion because it leads to this metallic contamination. Adding a screening oxide can sometimes help reduce that that metallic contamination. So with that, we will end this lecture on ion implantation. In the next lecture, we'll look at some of the more advanced concept of ion implantation and also look at repair, which is a very important aspect.